All right, let's do number 62. In the what if section of the example 4.5, it was claimed that the maximum range of a ski jumper occurs for a launch angle at theta being given that by that equation, where phi is the angle that the hill makes with the horizontal in this figure, where I'm just going to draw it to you guys. Prove this claim by deriving this equation. All right, so let's draw the figure. So this is going to be the whatever. So this is going to be the ski jumper. This is going to be the angle, and this pathway. And let's say it has some initial velocity v naught with some angle theta. Um, I should call it theta naught, but whatever. Anyway, so this, let's say it goes to its highest path and then it lands somewhere in here. The question is, in the what if section, and let's pretend this is the figure here, of the ski jumper, what is the maximum range of that angle depending on phi? So I encourage you guys to pause the video to give this a shot. So how the heck do we even find this? Well, we use the tools of mathematics. So like we've been doing all this time, folks. So if you're perceptive, let's say that this right here is going to be some length L. L is dependent on X, ow, and Y. X is going to be V naught cosine of theta times T. Forgive me, folks, but that's the condition I have. Oh, and I forgot to put my variables here. So let's say that this is going to be the distance D, and this is going to be the H. So Y is going to be H, and you can draw it however you want, but this is the way I'm gonna call down negative just to keep the orientation correct. Or you can call up negative and put a negative and then the negative and the plus for the gravity or whatever, but that's just gonna make it all confusing. So let's just keep this consistent. So B naught sine of theta times T minus gt squared over 2. So these are the general equations that we're going to be starting out with. However, I'm going to modify this because I want the equations to look simpler as opposed to more complex. So before I start, let me just modify this equation because I don't want to have to deal with the angle. But our overall goal is to get this in terms of one variable. And we're going to put the time, we're going to put h0, we're going to call this point position 0, and the time it takes for it to reach at that point. And we can find that time by taking that x, that distance d, divided by the constant velocity of the constant horizontal velocity. So that being said, folks, let's kind of like draw this. Let's just say, for the sake of simplicity, let's say that Vx is going to be V naught cosine of theta, and Vy equals V naught sine of theta. And the reason for that is because I don't want to worry about the angles. I don't want trig upon trig upon trig. I want to keep them separate, just to simplify this a little further. And I'm not sure what I'm going to do. I have my notes here, but then I threw it away. So I'm kind of re-deriving this as I'm doing this video. But I think I know what I'm going to do. I am going to... Alright, this is what I'm going to do. I'm going to solve for t here, and I'm going to substitute it there. So let's start with there. So I'm going to put h. So I'm going to take this equation, and I'm going to solve for t, and t is going to be x divided by v naught, or vx. So I don't have to worry about the components. So v naught y, x divided by vx minus g over 2 x over vx square. So that means that you have this equation, h plus by over vx times nx minus g over 2 x square over vx square. Eventually I want everything in terms of one variable. So so we're going to use another trick for this, and that trick is going to involve the, so I'm just going to move this out of the way. And I'm going to use this right here. I'm going to call this the length L, so I can define this to be the length L is going to be, I'm going to write this sine of theta cosecant of theta, so it's going to be h cosecant of theta, and L is going to be d secant of theta. And the reason for that is because I want to be able to replace all those variables. So I'm going to say that this is going to be L sine of theta equals h plus vy or vx. We're not going to worry about those. We don't care about those. We're going to treat those as a constant for now. This would be L cosine of theta. Notice that I'm substituting everything into its proper variables. And notice that, oh, and this is phi, not theta. Let me write this and then I'll change it here. Minus g over 2 vx square L cosine of phi. So this is phi, and this is also phi. There we go. All right. Oh, and this is going to be square. There we go. All right. All right. So I guess we're going to treat that trig as a constant. So that's our goal, folks. Our goal is to treat a specific variable as a constant so we can solve for this. But what I want to do first is I want to solve for L. So that's our overall goal. Let's solve for L. Let's just rewrite this equation as sine of phi, and I'm going over the algebra steps, folks. Normally I don't do that, but I'm going to make an exception for this video so you guys can follow along. Cosine of phi minus g over 2 vx squared. L is already going to be on the side. L cos square of phi. There we go. Now we can solve for L. And notice that solving for L should be pretty straightforward. And I think I messed up. Yes, I did. So, all right, I kind of had to fix the variables a bit. So yeah, I'm calling that 0. So yeah, this is the general equation that we're going to need. So so we're going to set y equals 0. We're going to replace h and x with these variables. And then we're going to set this equal to 0, and we're going to solve for L because that's our overall goal. And now notice that all this, if you move this on one side, and this take off the negative, everything will be positive. So that's really nice to work with. So let's just say that L is going to be, I'm just going to copy and paste this, sine of phi plus vy over vx. We're not going to worry about that just yet. And we're not even done yet. Our goal is really just to solve for this 2 vx squared divided by g cos square of phi. And that's it, folks. So let's kind of write this. So let's kind of simplify this. So now since we got the equation out of the way, 2vx squared divided by g cos square of phi. I know my thing looks sloppy, but that's okay. I'm going to make this look nice. We don't care about the phi. We're going to treat the phi as a constant. So so we're not really going to worry about that. In fact, the only thing we're going to distribute is this. So let's just write this as 2 over g secant of phi. We're going to keep that separated. We don't want to put tangent and secant. Well, let's just or 1 over cosine. Let's just keep that variable separate. So we're going to put the constant right here. And Vx, I am going to actually replace that with the initial velocity square over cos square of theta. So notice, folks, that Vx, I'm going to distribute it, and I'm also going to replace it Vy divided by Vx is just going to be V naught sine of phi, no, sine of theta divided by V naught cosine of theta. So that's just another way of saying this constant is out in front. This right here is going to be tangent of theta. So now we have an equation of L depending on phi, and so now since we have this equation, all right, so now since we have, all right, so we are going to treat this as L depending on phi and theta, but we're going to treat phi as a constant. So in other words, let's do this. Let's take this equation and take this to derivative to respect to, once we do that, dl d theta, let's apply the rules, and you can see why I put the variables as a constant. What we're really doing is we're taking the partial derivatives, but I'm just pretending that this is a derivative, and it's really the same thing. Oh, and this right here, let me take that off because that constant is supposed to be out in the, so let's take this off. So let's put this constant where it belongs. There we go. So this is going to be V naught square. So all right, now let's take the derivative. Now this is really nice because, oh, and actually let me change this too. Let me change this equation into something that we can take the derivative very easily now. And let's just say that this is sine of 2 theta to make this look really nice. All right, we're almost done. So 2 phi, 2 cosine of theta with the negative sine of phi sine of theta. There we go. There's the derivative. Now, on this one, this is pretty straightforward. The cosine of phi is the constant value. And we're going to bring the 2 out in front, which cancels with that other 2. And we're going to take this as cosine of 2 theta. And we're going to set this equal to 0. And when we do that, let's rewrite this as cosine of phi cosine of 2 theta equals sine of phi sine of 2 theta. Because regardless of the equations, when the maximum range for L is depending on when this is 0, where this equation will always have to be valid. So now let's just say that, how are we going to rewrite this? So let's just write this as tangent of theta. So let's just say that tangent of theta has to equal, oh my god. That's okay. I meant to say phi. Cotangent of 2 theta. I already lost track there. Regardless of whatever these equations look like, tangent of phi would have to equal this equation. So now since we got everything done, our goal is really to get to here. But here's the thing. We have to find the relationship between tangent and cotangent. And in order for that, we're going to need to look up some trig identities. So we're going to have to do a bit of Google because I don't have these memorized. So let's look them up and see what we. So let's take this identity and replace it. So tangent of theta tangent of phi is going to be cotangent of, or in this case, tangent of pi over 2 minus 2 theta. This is what we need. This is the key point right here. So now, since we have them all in the same trigonometry, which is perfect, let's just say that phi is depending on pi over 2 minus 2 theta. I don't know if this is correct, but let's see. It's not, but okay. But we're getting there. So we're going to solve for theta now. So we're going to take phi divided by 2. We're going to put that on one side. We're going to minus this part. And this would be pi over 4. And what do you know? This matches to theta. So what we did, folks, is we just proved to us, using the tools of mathematics, that the maximum rate for the ski jumper, depending on this phi, is related to this formula right here. Notice how beautiful this is, folks. Notice how easy it was for me to derive it, presuming the fact that I already made a lot of mistakes throughout this video and I had to correct it because I lost track of what I was doing and everything. And but you know, but that's common. I mean, you know, we're talking about algebra, and I'm also doing videos as I'm like doing these, but the overall concept is the same, folks. Solve for the time, replace it, get your equations, get it in terms of L if you want to. You don't really have to, but I just like to do that just to be consistent. Understand that, or I guess you could just keep it as X and Y. I guess you don't really have to replace it, but we do want to replace the L, so we do need that trig in there. Take the derivative to respect to those constant variables. It might be easier to do that first, to be honest. But regardless of how you approach this, the results should be this in the end. Because math is beautiful. I mean, I don't know about you, but I mean, folks, but math is wonderful. Anyways, I hope you enjoyed this video, guys. I'm going to see if I can redo this, but for now I'm going to upload what I have. Anyways, enjoy. Goodbye. I hope you guys enjoyed this video. Goodbye.